Hello, pre-calculus students. Please excuse this format. Just for the next week, I'm going to have to make do with this. So let's see. So about partial fractions. First of all, you should know there's 4 types, okay? When you have just linear factors raised to the first power, when the irreducible factors are some of them quadratic, like x squared plus 1, that's an irreducible quadratic. When all of those are just raised to the first power, or if you have linear factors, but maybe one of them raised to a higher power, or when you have one of the quadratic irreducibles, like x squared plus 1, raised to a higher power, say 3 here. So those are the 4 different ways these problems get broken down. And for each one of those, there are 2 different versions of solving them. So let's look at example 1. This is of type 1, and I'm going to show you both ways of solving it. And in this case, those 2 versions are equally easy. So if you had 5x plus 7 over x minus 1 times x plus 3, if you want to decompose that into partial fractions, you want to find 2 fractions involving those 2 factors as the only part of the denominator, and you want to find a and b so that this equation is true. All right, so why would you want to do this? Just wait till you get into Calc 2. You're going to be, instead of integrating this whole mess, integrating these 2 would be a lot easier, where a and b are some constants. So let's find those constants a and b. That's what we're doing with partial fractions. Notice that if we combine these, giving them the like denominator of their product, we would have this statement: this rational expression equal to that one. With the denominators are exactly equal, that forces the polynomials in the numerators to be equal. All right, so now we're trying to solve that equation. When is 5x plus 7 equal to a times x plus 3 plus b times x minus 1? And you can factor the a through there and the b through there and gather like terms. So the linear coefficients will be a plus b. The constant coefficient will be 3a minus b. When is this polynomial equal to that one? Only when that linear coefficient is equal to 5, and only when that constant coefficient is equal to a 7. So for that equality of polynomials to be true, the linear coefficients need to be equal and the constant coefficients need to be equal. In other words, this equality between polynomials is true only if a plus b is equal to 5 and 3a minus b is equal to 7. 3a minus b is equal to 7. Okay, so those are 2 equations that we want them both to be true, so that's called solving a system of equations. Now this one is just what we call a 2 by 2. 2 equations and 2 unknowns. Lots of different methods for solving those. Elimination is one of them. This one, it's easy to eliminate the b. If you add the 2 equations together, you get 4a equal to 12, so therefore a has to be a 3. You substitute that back into one of the equations, and you'll get b is equal to 2. So therefore, we have decomposed this rational expression into these 2 partial fractions, these 2 partial rational expressions. And again, you'll really appreciate being able to do this quickly when you get into Calc 2, because instead of working on that integral, which is no method for solving it, you've got these 2, very easy for you to solve. What's that other way of solving example 1? Well, it's the same up to that polynomial that you're trying to solve for here. I'm trying to solve for a and b in this polynomial. So I'm just repeating that line from version 1. The difference with version 2 is that if instead of just going to solve a system of equations straight up, here you try to, and sometimes this works more spectacularly than others. I'll give you an example of that soon. But you try substituting in a value for x. That reduces a lot of terms, okay? So again, we're just trying to make this polynomial equal to that one. if those two polynomials are equal, if polynomials are equal, that means they have the same value for every value of x. So let's substitute in a value of x that gets rid of a lot of things, like x equal to 0. If you substitute x equal to 0 into that, you end up getting 3a minus b is equal to 7. Okay, now notice if you try substituting in the value x equal to 1, this, substituting into this double star equation x equal to 1, you get, oh, this one's a lot faster. It just gives us, it reduces much more nicely, and it gives us a is equal to 3. Now you could go back to that line there, substitute in a equal to 3, and just as in version 1, you get b is equal to 2. So you didn't buy much by looking at that other method in this example. Here's an example where version 2 is decidedly better. By the way, where am I getting these examples to play with? Your textbook, the electronic file for it on my math lab, has an exercise set, just like there's an exercise set at the end of every section in the book, physical book. There's an exercise set in every section of the e-file version of the book. This is number 36. Asks you to find the partial fraction decomposition of that over that. Now you'll notice that this one hasn't been even factored in the denominator. What? In pre-calc, they're going to expect you to be able to factor something with 4 terms? Yes. If you remember your college algebra days, there's all kinds of ways to get started. You could think about the rational roots theorem, which should be called the possible rational roots theorem, and using synthetic division, all kinds of things. Oh, but remember, there's factoring by grouping. So if you factor by grouping, you find out that that denominator polynomial factors into x plus 2, which is a linear irreducible polynomial, and x squared plus 4, another a quadratic irreducible factor. So it's another irreducible, but this one's quadratic, okay? So we're going to try and decompose this into something of this form. Now you'll notice this is a type 2 partial fraction problem. I do still have a constant over the a of the x plus 2, that linear factor, but this time my irreducible is a quadratic. So I put a linear polynomial, unknown polynomial above it, bx plus c. Okay? You'll notice that this constant polynomial here is of degree 1 less than the denominator. Same thing is happening here, right? This is degree 2, so you put an unknown polynomial of degree 1 above it. That's true for any type 2 problem. So we're going to decompose this rational expression. After we factor the denominator, we're going to decompose it into the sum of these two. All right? Well, when could this happen? Now these denominators are exactly equal, right? This is just the factored form of that. We just need this numerator to equal what the numerator would be over here if we combined found a common denominator and combined it again. So we get 3x squared minus 2x plus 8. The known numerator polynomial would have to be equal to a times x squared plus 4 plus bx plus c times x plus 2. Okay, so again, we're trying to figure out for what a and b are these two polynomials exactly the same. If you multiply this out and collect quadratic terms, linear terms, constant terms, you'll notice that gives us 3 equations in 3 unknowns. Okay, so the quadratic coefficients add up to a plus b on the right. They have to be equal to 3 on the left, first equation. What are our linear coefficients? Just 2b plus c. So 2b plus c on the right-hand side has to be equal to minus 2 on the left, and 4a plus 2c has to be equal to the constant term over here, 8. Well, if we clean that up so it looks like 3 equations and 3 unknowns in the most general form, That takes a little bit of work. Using matrix methods, right, just peeling off all the coefficients, you can show that the row reduced echelon form of this, in other words, with just all nice ones and zeros form, looks like this. And what does that tell us? That tells us that 1a is equal to 3, 1b is equal to 0, and 1c is equal to -2. By the way, if you want more on this type of method, you can look at my 1324 videos, where there's a video there about how to do this method by hand, or to use a function in your in a graphing calculator like a TI called RREF. It just gives you those numbers. So there's a lot of scratch work I'm hiding in here, right? So the first method, certainly not as easy as the first example where we were just dealing with a 2x2. So this example shows us where version 2 is really much nicer sometimes. So again, going back to the equation where this polynomial, we're trying to solve for a, b, and c so that this polynomial is equal to that one. Again, one polynomial is equal to another polynomial only if they have the exact same values at each substituted value for x. So we can plug in values of x that make our lives easier. So for example, see that x plus 2? If we plugged in x equal to -2, that would become a 0, times this would make this whole thing 0, right there. So if we substitute in x equal to -2, that equation reduces to something that's just one equation and one unknown, and we get a is equal to 3. So now we take that same star equation, replace that a with a 3. Now we've got an equation with two unknowns, b and c. What value of x would get rid of a lot of noise? X equal to 0 is always everybody's go-to. So we'll try that. If you let x equal to 0, everybody on the left-hand side goes away but the 8. On the right-hand side, lots of things go away, but just this. And you're able to solve for c. C is equal to -2, a is equal to 3. Go back into the star equation and replace that a and that c with those values. And now you're looking at it going, what's going to make my life easy? What value should I substitute in now? Well, if you've already done 0, the next one, usually everybody's favorite, is 1. Okay. Why didn't we start with those first? Why didn't we start with -2 here? Because there was a factor, x plus 2. If we can zero out a whole factor, that's usually going to be reduce the equation the most. So here, if you plug in x equal to 1, that's easy for everybody to do, and you end up getting an equation for b. Oh, b has to be equal to 0. So now I'm going to give you a third example, because after I show students that second version where you plug in some values, 0, 1s, whatever, a lot of students just want to use that all the time. Here's an example where that version doesn't get us anywhere nice. And this is also a different type of partial fraction decomposition problem. So notice we have here a linear factor, x minus 8 is being raised to the third power. This is a type 3 problem. Look how we have to set it up. That x minus 8 is a linear factor. It's here raised to the third power, so we have to have it raised to the first, the second, and the third power. So we have 3 separate partial fractions. Okay, so if you made this into one rational expression on the right-hand side, it would force you to multiply this one top and bottom by an x minus 8 squared, this one get multiplied top and bottom by an x minus 8, and this would not be multiplied by anything. And so the numerator of the right-hand side equal to the numerator on the left-hand side would give us this polynomial has to be equal to that one. I'm going to show you what what version 1 looks like first. If you take all the quadratic terms and set them equal to the quadratic coefficient here. Quadratic coefficient here is a. Quadratic coefficient over there is just a 1. Oh, sorry, that's what I'm doing right here. So here's all the quadratic coefficients set equal to each other. Here's the linear ones set equal to each other. Here's the constant ones. So that is technically 3 equations and 3 unknowns, but luckily for us, one of them is already got the answer. So if you have a situation like this, version 1 is the way to go. You just simply back substitute. A equal to 1 gives you that equation 2 looks like this, and that gives us b is equal to 13. Substitute in both of those, and you're going to get equation 3 has this result. Oh yeah, c is equal to 45. So this way, solving the system of 3 equations and 3 unknowns wasn't too bad. The numbers were nice. Okay. Why doesn't version 2 work so well here? Well, let's see what happens. So again, we start off with this polynomial, setting the 2 polynomials equal to each other. And we think, okay, what would be a good value to substitute in here that's going to make a lot of terms go to 0? Well, if we can zero out these 2 by setting x equal to 8, okay. This time we're going to get c equal to 45 as our first value. All right, so if you plug that in to there, you're looking at this equation. Excuse me, if you plug this c equal to 45 into that equation here, you're looking at a similar equation just with 45 there. So what's an easy number to plug in? How about x equal to 0? Everybody's favorite. You plug that in and you end up getting an equation with 2 variables, two unknowns, two unknowns, a and b. What else should we substitute in? We already did 8, we've done 0, well, let's try 1. And of course, using c equal to 45. So if you plug that in, that's not very satisfying. So we have simply reduced our system of 3 by 3s, which was nice, to a really nasty looking 2 by 2. Again, if you know how to use, you have a device that does solving systems of equations for you using our REF, okay, that's fine. But really, version 1 was preferable here. One quick little note here, whatever you decide the unknown coefficients are, you should run a partial check. This is something you can do speedily that can catch really gross errors. So we were thinking a is equal to 1, b is equal to 13, c is equal to 45, but before we enter that as our final answer, we might want to check it by asking ourselves, does this equal that? Rather going through all the algebra, you can substitute in a value. So what happens when x is equal to 0? You get an equation, is the left-hand side still equal to the right-hand side? Asking, and you can check, oh yeah, so that worked out okay. And that gives you a little bit more confidence that your answers are correct. Okay, it's not complete proof, but it can catch those errors which can populate in this type of solving a system of equations problem quite easily. Okay.